Hi there everyone, welcome to a very short video on DC circuits, simple single component circuits. This video is intended as a quick refresher into some of the formulas and some of the applications of those formulas for very simple circuits with single components like a single resistor and a battery. So just as a quick reminder, we've got our basic single component circuit here on the right. It's a resistor in this case connected to our battery. And the resistor is connected via wires and the battery acts as the EMF, the source. The resistor can also sometimes be called the load. Typical questions you might be getting asked at sort of basic electrical principles level courses will include things like denote the difference between conventional current flow and electron flow, or explain the difference between them using the aid of a diagram, and so on. So in that case, what you do is you draw something that looks a bit like this, and as a reminder, conventional current flow flows from positive to negative. We think of it as the positive charged particles, or the positively charged particles flowing from positive to negative, as denoted by our little red dot here moving around the circuit. And conventional current flow was traditionally, or is traditionally, used in engineering-based subjects. It's what people thought electricity was initially, this flow of positively charged particles. However, what was later discovered was actually this was incorrect, and actually it is electron flow, which is what's actually happening inside the circuits, and that is the flow of negatively charged particles, what we call electrons, flowing from the negative terminal around to the positive terminal of our battery through the circuit. So we're going to be doing some basic calculations on circuits like this, and you're going to need some formulas for those. And just a reminder, we've got Ohm's law, V equals IR, voltage is current times resistance. We've got P equals IV, which is power in watts, is current times voltage. We have energy is equal to the power times time. Energy measured in joules, power watts, and time in seconds. Now sometimes you might see this denoted as a W for the energy instead of E, W for work. That's absolutely fine, whichever one you're more comfortable with, or whichever one you're using, just keep using that. And finally, we've got charge is equal to the current times time, Q equals IT. Charge is measured in coulombs, current again in amps, and time in seconds. So let's take a look at our first practice question here. I'm going to do this one in real time with you on the board, and then I've got 5 questions, tutorial questions for you guys to try. I'll let you guys have a go at them first, and then I'll quickly put the answers up, chat through them at the end. Right, so practice question here. The 12 volt battery is connected to a 10 ohm resistor. And the first part of the question is we're asked is to sketch a diagram of the circuit, label all the components and their values. Okay. So we're going to start by drawing our 12 volt battery, which is connected to a 10 ohm resistor. So we can draw a resistor here, which is just going to be a simple rectangle. We can note the value of it on the diagram, which is 10 ohms. We draw our battery. The positive terminal is always the longer terminal, which is denoted with a little positive, and the negative terminal is the smaller one, the shorter one. So we can then draw our wires connecting it up, and I've got to label up my voltage here, which is 12 volts. So our supply voltage here is 12 volts. Okay, so that's us labeled up our diagram. Part 2, identify using the diagram the difference between conventional and electron current flow. Well, that's what we just did in the previous slide there. We can denote conventional as flowing from positive to negative. That's what this little arrow here means. So we can label up and say, well, that's conventional. And then we can show our electron flow as a second arrow on the other side here, electron. Question 2 done. Determine the current in the circuit. Well, this is where we're going to use Ohm's law. If you remember, we have V equals IR. We want to know what the current is. Well, we've got the resistance and we've got the voltage. So we're going to rearrange by bringing R underneath, by dividing both sides by R effectively, to get our I by itself. So in this case, our current I is going to be V divided by R. So we can substitute the values in. So our voltage was 12, our resistance was 10, and we get 1.2 amps. Calculate the charge that left the battery after 1 minute of running. So you remember that charge is a measure of coulombs, which is effectively a measure of the number of electrons or charged particles you have in one place. So what we're really doing is seeing how many electrons have moved through the circuit in a given amount of time. Charge is Q. In this case, the current we've just worked out, which is 1.2 amps, multiplied by the time. Now, we always have to put our time into seconds unless the formula specifies otherwise. So in this case, 1 minute is made up of 60 seconds, so we're going to have to multiply this by 60. And that will give us 72 coulombs. Question 5, determine the power of the resistor. P is equal to IV, and in this case our current is 1.2 amps, multiplied by the voltage of 12 volts, which equals 14.4 watts. In question 6 here, calculate the energy consumed by the resistor after 1 hour of operation. So straight away it's asking us for 1 hour of operation. Well, we need to convert that into seconds. So our time in seconds, well, 1 hour has 60 minutes in it, and each minute has 60 seconds in it. So that's going to be 1 for the number of hours times 60 times 60, which is equal to 3,600 seconds in our hour. Energy, or E, is equal to the power times time. So in this case, our power was 14.4 multiplied by our time of 3,600 seconds, which equals 51,840 joules. If we were converting that into engineering notation, which I'll do, 51,000.8 kilojoules of energy. So on screen right now, I've got 5 tutorial questions that I think you should have a go at. You could pause the video here, watch them, look at them on screen and have a go at them. Or if you go into the comments down below, you'll find a link to a PDF of the same 5 questions. And then once you've had a go at them, come back to the video, you can watch the rest of it where I go through the solutions to all 5 of them. Okay, welcome back. Hopefully you've had a go at those 5 tutorial questions. I'm going to run through the solutions now. Because we've already gone through the practice one, what I'll do is I'll just put all the workings up on screen and then quickly talk through it so you can see the solutions. We were given a simple circuit. The battery is 24 volts and the current is 1.5, and then we're asked to calculate each of the following. So we've got marks available for each of these now, and just a quick comment on that. The way I've allocated marks here is the way that I would allocate marks when I was writing an assessment, and that kind of falls in line with SQA guidance in terms of higher physics, advanced higher physics and engineering based subjects, which is you get a mark for the right formula, you get a mark for a correct substitution, and you get a mark for a correct final answer. So you would see in the case of part A here, there'd be a correct mark for the formula, and you would get a mark for either writing V equals IR or I is V upon I, R is V upon I. You would get a mark for the correct substitution, so correctly substituting in 24 for the volts, 1.5 for the amps, that would give you another mark, and then finally a correct answer at the end with the correct units, so 16 ohms would give you the final third mark, so that would give you 3 marks for that question there. Different places, different institutes, different lecturers will award marks differently, and you kind of just need to learn how they award marks. What would encourage all students to do though is ask the lecturer directly, where do I get marks for, where do I get marks in this question? What do I get marks for in this question? To help you know when you're getting marks and when you're not getting marks. Okay, part 2 or part B here is power, P equals IV. So substituting our current of 1.5 amps multiplied by the voltage of 24, so we get 36 watts. Again, a mark for the formula, a mark for the substitution, a mark for the correct answer with units. And then energy is power times time for part C here, and that's 36 times 8 minutes times 60 to convert into seconds, gives us 17,280 joules or 17.3 kilojoules. If you're not sure what I did there, basically what I've done is I've rounded it up into the kilo. I've basically put it into engineering notation to factor of 3, because 17,280 joules isn't a very useful number, whereas working with 17.3 kilojoules is easier to do. So that's what we've done that for. So again, mark, substitution, answer with units. Now, what I'll say on this is depending on the level, you may get penalised for not putting it into engineering notation. Again, look at the course you're doing, look at the level of the course you're doing, and speak to your lecturer. At lower levels like electrical principles, level 5, level 6, NC levels sort of courses, you won't be getting penalised if you just leave it in this answer here. That's absolutely fine. But generally speaking, higher levels, they'll expect you to be working in engineering notation. Question 2. A simple circuit has a resistance of 100 ohms and a current of 2.1 amps. Determine each of the following: the voltage of the battery, the power of the resistor, and how long the circuit must run to consume 1000 joules. Part A, work out the voltage over the battery. So we know the battery is driving 2.1 amps through the circuit, and we know the total resistance of the circuit is 100 ohms. So we can use V equals IR to determine what voltage is being driven by the battery. So in this case, that's going to be 2.1 times 100, so that's 210 volts. So mark, 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 3 marks. Part B, power of the resistor. Well, we need to know what current is flowing through the resistor. That's the supply current here, 2.1. And we need to know the voltage over the resistor, which is 210 volts. So 2.1 times 210 gives us 441 watts. So mark, mark, mark. Part C. So this is a slight variation on the typical question. Now we've got to work with energy and rearrange to get time. In the last question, we were given time and power and had to work out energy. So now it's a slightly different rearrangement. So I've gone ahead and rearranged the formula. So our time is our energy divided by power. So it's a mark. So we divide our energy of 1000 joules by 441 watts, and that gives us a mark. And that gives us 2.2676 seconds. Now I've just written out 4 decimal places here in the calculator. What I'll then do is I'll then round that up to 2 decimal places here, 2.27 seconds for that. Again, make sure you're following what your lecturer is saying. What are they typically doing in class? Are they going to 2 decimal places, 1 decimal place? What's their preferred method? Ask them directly. Do you want me to go 2 dp? Do you want me to go to 3? And then they'll tell you what their preference is. And that again is our 3 marks. Question 3. A simple circuit has a resistance of 1.2 kilo ohms and a supply voltage of 12.5 volts. So let's just focus on this resistance here. The K stands for kilo, and that is times 10 to the power of 3. So we can either write that as 1.2 times 10 to the power of 3 or 1200 ohms. And then we're asked to determine supply current, charge that's moved through it, and the power of the resistor. Okay, so let me just talk through a couple of the reasons for the decisions that were made here and why we got the values that we did. So for part A, we had to work out our current. So for that, I rearranged Ohm's law, voltage divided by resistance, 12.5 over 1200. Now, you might get something that looks like that in the calculator, and depending on what level you're doing this subject at, and in this case I'm sort of pitching this at a very introductory level for electrical engineering, so maybe NC level if you've just started doing this, then you may get away with leaving the answer in this form. However, what you need to start doing is getting into the habit of putting it into engineering notation. And if you're not sure how to do that, there is actually a little button on your calculator. If you just push the ENG, if it's a scientific calculator, that'll transform your answer from this into an engineering notation answer. However, you just need, this is something you will need to practice and get better at doing. The way to do it manually is you can actually count in terms of multiples of 3. So if I want to make this a quote-unquote bigger number, I just count down 1, 2, 3, and so that moves the decimal point down. So going from normal number down to milli, okay, times 10 to the minus 3, 10.42 times 10 to the minus 3 amps. Part B, Q equals IT, my charge. So again, we use that current. The reason I wrote it like this is because I was representing the fact that I kept it as what was in the calculator, and I used that number to be more accurate when I did the next stage of the calculation. So that then gave me 3.125. I've then rounded that to 2 decimal places, 3.13 coulombs. So we get our mark for the final answer, substitution, and formula. Should say here as well, formula, substitution, and final answer. Then P equals IV, power is current times voltage. Again, I'm using that same number that was stored in my calculator to keep the accuracy as high as possible, multiplied by 12.5, and then I've rounded that to 2 decimal places, 0.13 watts. So answer with units, substitution, formula. Question 4. A simple circuit has a battery of 6 volts and after 4 minutes has consumed 200 joules of energy. Question 1. Sketch a diagram of the circuit. Then using the diagram, explain the difference between conventional current flow and electron flow. And then for part C, determine the power of the circuit. Part D, calculate the circuit current. And part E, the circuit resistance. Okay, I'll go ahead and do that and I'll be back with you in a second. Okay, so welcome back. Let's just run through these questions. So I've sketched out the diagram and let's just see where we're getting the marks for this. Well, I've got my resistor, I've drawn the right component and I've also labelled it, so I'm going to get a mark for that. I've drawn my battery, I've drawn it correctly, I've got my bigger terminal as a positive, I've got my smaller terminal as a negative, I've labelled it correctly and I've given it the right value. So you might be wondering, where do I get the third mark from? And this can vary. So some places, some tests might award a mark for neatness. So if you've drawn it neatly using straight lines, a ruler, that sort of thing. You may also get a mark for just drawing in the wires. Again, just check with your lecturer, see what they're awarding marks for, just so you know where it's coming from. But that's where the 3 marks are for here. For part B here, we were asked to then use the diagram, and with the aid of the diagram, explain the difference between conventional current flow and electron flow. And just a wee note here, just to draw your attention to, the key word here is explain, okay? So if we're asked to explain something, that means we have to give a written explanation. We can't just give a bullet point, and we can't just rely on the diagram by itself, okay? And we kind of covered this question already, so I'll just go through it a bit more quickly, just to say that conventional flow is that positive charged particles moving from positive to negative, whereas our electron flow is the flow of negatively charged particles, electrons, I didn't put that in there, but I should have, moving from the negative to the positive. Okay, so you can see here where we're getting the marks. If I highlight them here. So we've identified on the diagram conventional and electron flow, so a mark for each of those, and then we've correctly stated what each of these things are, so we're getting another couple marks for those as well. Part C, we need to work out the power of the circuit. Now your first instinct might be to go to this formula here, because that's the formula we associate with power. But actually we don't have enough information here to go ahead and work that out. We don't have the current yet. So we've got to think elsewhere, and that's where this formula comes into it. E equals P over T. We do have energy and we have the amount of time. So we can rearrange that to get E over T. Substitute our values in of 200 over 4 times 60 for seconds. And that gives us 0.83 watts. So there's our 3 marks. Part D, hopefully you managed to get this one as well. Rearrange P equals IV, so P divided by V voltage gives us 0.83 over 6, which is 0.1339 amps. On my calculator screen it was 0.13888 recurring, so I rounded that to 9. And then I've converted that from amps into milliamps. Again, going back into engineering notation. Then for resistance, we've got R as V over I, in this case 6 for a voltage of 6 volts, and divided by our current that we just worked out of 0.139 amps, and that gives us 43.2 ohms of resistance. So we've got our final answer with units, we've got our substitution, and we've got our formula here. Question 5. So the supply current is 600 milliamps, so that's 600 milliamps. Remember, milli means times 10 to the minus 3, so that's times 10 to the minus 3 amps, which equals 0.6 amps. So if you type this into your calculator and hit equals, it'll translate it into 0.6 amps. Or you can just remember that 600 times 10 to the minus 3 means that the decimal point moves 3 places to the right. So if it's 600, we move 1, 2, 3, so the decimal point goes there. We then draw a 0 in front of that and it becomes 0.6. Okay. And the circuit consumes 5.5 kilojoules of energy. Again, kilo times 10 to the 3 this time, so that's 5.5 times 10 to the 3. The decimal point moves in the opposite direction this time, so 5.5, 1, 2, 3. Anywhere there's a gap, we write a 0, so this becomes 5,500 joules. And then that consumes that energy in 30 seconds. All right, so there we go. That's the final question here, and you can see this one's a little bit trickier in that you need to rearrange some of the formulas, and it's not always the first formula that you might think about that we use to solve the problem. So for part A, we were asked to calculate power in the circuit. So rather than using our standard P equals IV, this time we have to use E equals PT and rearrange to get our P. So we do that, we substitute in our values. Our energy is 5,500 divided by 30, and that gives us 183.33 watts. I suppose for consistency here, I've gone to single decimal places, so I should really, to be consistent, I should get rid of that 3 and just leave it there. So we get an answer for our final answer with units, we get our substitution, and we get our formula here as well. Then we move on to part B here. So here again, not as straightforward as before. We're using a different formula than maybe we would first think about. We've got to use P equals IV. And what I'm doing here, what you see me doing, is I do a little tick above the values that I've got, because that once I know that I've got 2 out of the 3, that means I can use that to get a third value, to get the unknown, basically. So I rearrange for V, P over I, substitute in, and I get 305.56 volts. And again, I summarize that down to one decimal place, 305.6 volts. So we get answer, final answer of units, substitution, and our formula. And part C, determine the resistance of the resistor. Well, Ohm's law, rearranged, voltage divided by current, 305.6 divided by 0.6, and we get 509.3 ohms of resistance. So again, mark for the answer, mark for the substitution, and mark for the formula.